Okay, recording started.
All right. Hello, everyone, and welcome to the February CARC Systems Facing track call. Today, we'll be showcasing the Rogues Gallery. So this is a NSF-funded project run by Georgia Tech's Center for Research into Novel Computing Hierarchies. The gallery is an experimental testbed concept focused on developing our understanding of next-generation hardware with a focus on unorthodox, uncommon, or rogue technologies. Dr. Jeffrey Young is the co-director of Georgia Tech Center for High Performance Computing and also director of the novel architecture testbed, the Rogues Gallery. And we'll be discussing some of the insights that he's had so far in running this project. Dr. Jeffrey Young.
Okay, thank you, John. And thank you everybody for joining. I really appreciate it and appreciate this opportunity to share with you all. I want to note before we get started that I guess I'm PI of the NSF project and unofficially director of the testbed. But I'd also like to thank Aaron Jesgani, our PACE scheduler architect, who helped out with a lot of these slides from different presentations, as well as our co-PIs, Tom, Ada, Jennifer, Rich, and Alex Sterling as well. Okay, so we'll get started. So we have kind of an overview. So hopefully I'll keep this talk, maybe about 30 to 40-ish minutes. We'll see how it goes. But please feel free to stop me at any time if you have questions. And I'll try to keep an eye on the chat and see if I can stop and answer questions from folks. So we'll kind of do a brief overview. We'll talk about this concept of what we call novel architecture workflows. An example of that for the Lucada Pathfinder. Talk about education. That's one of the big things that we do with this testbed. Talk about integration with our large-scale compute with PACE. They're traditional, kind of more homogeneous HPC clusters and how those interact with this novel architecture testbed. And then just a few slides on kind of lessons learned and what we think we'll do in the future. Okay, so what is the Rogues Gallery and why is it called the Rogues Gallery? We had this idea, say back in 2017. We got a very unusual piece of hardware, and the center that it was hosted under, the Center for Research into Novel Computing Hierarchies, is meant to be kind of a across the stack kind of research center where you look at both, interesting post-more computing hardware, things that are relatively different from what we consider to be commodity today, but also the ways that you actually program and interact with those systems. So in our mind, these pieces of hardware were sort of rogue. They were things that no one had really said, I want to take these and put these into my data center and make them production resources. So they are kind of on the experimental side of things. The Rogues Gallery is a testbed that got funded in 2020. So we're kind of in the extension period, but are also looking to sort of enhance and sustain that project in the near future here. Currently, we have a large number of development servers, as well as a lot of small development boards. So we have things like Cascade Lake, Skylake, Ice Lake, AMD Milan, a few of the new AMD and NVIDIA GPUs. And actually, one of our IT people just sent me a picture of a Intel GPU that we're going to plug in here shortly, as well as kind of more unique things like RISC-V, FPGAs, and kind of novel graphic accelerators. So some of the pictures on the page here, we have stuff like ARM servers, the Lucada Pathfinder, which we'll talk about, SmartNICs, and RISC-V. So the name of the game here is that not only are these things weird, but this testbed is meant to be kind of a place where we can look at the idea of extreme heterogeneity. And we'll talk about what are some of the benefits of that, as well as what are some of the challenges for putting all those things in one testbed. So in a more graphical format, the testbed has a couple different pieces. When we wrote this proposal, we said, okay, there are like 4 or 5 areas that we want to focus on. And some of them were things that we locally at Georgia Tech already had some expertise in. So here we have neuromorphic accelerators, we have the field programmable analog array, which one of the co-PIs, Jennifer Hassler, has done a lot of work on, as well as near memory computing, with things like Optane and the Lucado Pathfinder. Those are both things that we were previously doing and thinking about, and we said, okay, it'd be great to sort of put these as part of a test bed. Then, of course, there's next generation aspects of kind of HPC type accelerators. So those are things that, might be, like ARM CPUs. If you remember back in 2020, those were a little bit less commodity. I think now, people are starting to see those as sort of things that they could put in a production environment. But at the time, I think even internally, we had some discussions that because of the difference in software stacks and some of the tools needed to run and maintain those systems, that they went more in this experimental direction rather than into our production test bed. And then kind of close to my heart, things like next generation, or what we call smart networking. I think initially we envisioned that we might have some 5G testbed aspect. The NSF actually funds several different kind of 5G, quote unquote, prototype 6G testbeds. So I think the other thing we realized that is really hard to do those in a remote fashion. So there are people working on some of those topics locally, but that's not currently a focus of the testbed. And then finally, we have things like what we call future rogues. So I put quantum here. I have things like cryogenic computing, reversible computing. We do not host the quantum computer, but we will let you run quantum simulations and look at quantum compilers and things like that. Part of that is just because right now running a quantum computer is sort of a huge effort in of itself. So we have all this interesting hardware on the right-hand side, but one of the things that I think is important to note is that the hardware is interesting on its own, but is somewhat unusable if you don't know how to use it, and if you don't have the pieces on the left-hand side here. So a lot of those are the pieces that sort of glue everything together, which we'll talk about a lot today, the HPC infrastructure, things like integrated front ends, for VMs and notebooks, training materials, especially, we'll talk about Jupyter notebooks, APIs to program some of these systems, and then finally sort of benchmarks and data sets for, sort of the target applications that we propose with this test bed. Real quickly, I just want to note that we have a nice diverse team of researchers. Myself, my background is kind of computer architecture and HPC, with a little bit of reconfigurable computing and smart, what is now called smart networking, I guess I should say. We have Tom Conti, who's an expert in computer architecture, Jennifer Hassler, who works in analog computing and neuromorphic computing, Ada Gavriluska, who's an expert in systems and kind of interesting near memory applications for systems, Rich Budick, who does a lot of HPC and architecture, Alex Douglas, who does smart networking, and then our wonderful tech support, Sterling, Will, and Aaron, who all contribute to kind of all of these areas of expertise. So they really are helping us build all the glue logic to put everything together. Few highlights, cool stuff that we think our test bed is pretty unique for having done. One of the things that I think we're really interested about, I worked with ARM HPC for a while, and we did kind of get an A64 FX system about the same time that Ukami came online. I think one of the interesting things we did with ours is that we put open on demand on it and looked at sort of some of the challenges of doing that. So we actually wrote a paper that I think came out in 2021. And then we had some good conversations with the folks at Recon. And obviously they did a lot of the work themselves, but it was interesting to talk with them. And I think before we talked, they didn't really have this idea that might be a usable and interesting user interface. So, they had sort of the traditional kind of HPC batch scheduling, but, maybe seeing one instance of that, even in a prototype phase, kind of encouraged them to deploy it on their system. We have one system, Lucado Pathfinder, that is on both the Graph 500 and the green Graph 500. For those of you who are really interested in graph analytics, we can dig more deeply into that. That's kind of an alternative benchmark that's been around, a little bit different than top 500, just because the people that are interested in graph analytics and that run graph analytics are typically a different group than the folks who are, running large-scale scientific simulations. But that's pretty nice. We actually work with Lucada to make those submissions. This number is probably up to date. We have something like 180 to 200 researchers, a large number of external users, and then obviously within both of those numbers, some of them are sort of super active, and some of them are kind of prototyping or slowly testing out some small feature they're interested in. One of the really nice things I think we can point to is that we have this educational infrastructure that's part of the testbed, and that supports our students. And as I like to say, it saves our students a lot of money every year. I think the number was something like 10 to 12K per semester, from not having to buy boards for certain labs. So that's something I think we're really proud of having done with this testbed. Other unique, interesting things. This here is a picture of one of our field programmable analog arrays, but obviously there are a lot of Department of Energy labs that have maybe bigger hardware or more expensive hardware, but I think we've kind of found an interesting niche for ourselves in terms of doing graph analytics, neuromorphic hardware, and smart networking. And we kind of figured out that if we try to integrate this with our local teaching and educational mission, this provides a really good way for us to do kind of beta testing and documentation. Because if the documentation is not up to par, these students will let you know, especially if their grade is anyway dependent on being able to use some of this interesting hardware. One of the other interesting things that I won't talk about a whole lot today, but we have a scientific software engineering center where I am also currently acting as a co-director. And so we're trying to think about how do we help scientists and researchers do a better job of software engineering for their projects. So I just want to speak about that because I'm really excited about that. And I think this is something that hopefully we'll have a paper demo shortly that I'm putting Sterling on the hook, and I think he's very interested to do. But we have kind of pretty good documentation for doing CI/CD runners on the Rogues Gallery. And for those of you who do GitHub development, you might know that this is kind of a big deal because traditionally you can run on sort of CPU-based web runners. But let's say you are writing a code that uses an NVIDIA GPU backend, or maybe you're looking to test something on RISC-V and see if it works consistently. So we've actually set up a sort of a development VM and a process, and hopefully pretty good documentation that lets you set up these novel architecture runners. So if you go and look at the page down here at the bottom, it is our read the docs. I know that's a long URL, but if you go there, it's sort of near the top on the table of contents, so you can go look it up. But this is actually one that I set up for a project I'm working on. So we have this benchmark called Spatter. And one of the challenges that we had is that we were working with some of the DOE national labs, and they said, this is cool, we like this benchmark. Can you please add some tests for NVIDIA GPU and maybe AMD GPU? And how about Intel GPU as well? And, obviously we don't have all those, but, for the ones that we have, we can now sort of set this up and have it run, maybe once a day and say, okay, are all the commits to the CUDA backend still working? So we think this is a really valuable resource. We know other folks are looking at this in the context of their test beds, but we believe that because everything in our system is Slurm scheduled, that this is something that is a little bit unique and interesting. Okay. All right. So I'll jump into one of the things that I think is important to know about this experimental test bed, and maybe any experimental test bed, and that is the concept of novel architecture workflows. And we'll talk about it in the context of the Lucada Pathfinder. So when we talk about a workflow, really what we're talking about is that typically, with a novel architecture, depending on how novel it is, you might have something that is sort of simulation based, where maybe you run a subset of the functionality, but the performance is not guaranteed. Emulation, where you get some idea of what the performance is and the relative performance, but the actual timing and the execution is not fully correct. And then finally, you have sort of the performance profiling and optimization stage of, a workflow. And so we kind of label this as Rogues Gallery should help us support both simulation, emulation, and evaluation for as many architectures as we can do this for. So we'll go into an example here, but one kind of generic workflow is, okay, maybe I request a VM. I run a simulator that doesn't take a lot of memory, but maybe I just need to run it for a few hours. I check to see does that work correctly? If so, then maybe I go to some prototype hardware, possibly one node or a few nodes, and run and see if things work there correctly. Maybe I do some performance tuning, and then finally I might go to sort of a larger system, whether that is a large number of nodes or, sort of scale up to kind of a full device run. There are important things that we use to enable these workflows. We found that, these are sort of consistent, even though the technologies themselves are very different. One of the things that we try to do that we think is pretty cool is we try to Slurm schedule everything. Back in 2019, we wrote this paper and we said, well, we think this test bed would work, but the only way it's going to work is if we can get everything in a place where people can sort of request access. And, you can say, if I have a Raspberry Pi, people are not fighting over it and running the same benchmarks at the same time. So, one of the things that led to is that we said, well, even small devices, like things that are USB connected, if it can run, sort of a basic operating system, some applications, then we can potentially Slurm schedule it. So I had the example previously of the field programmable analog array. That's a USB device. The way we schedule that is we plug it into a Raspberry Pi. And so if you want to use that device, you get access to the Pi, and then you can run your test on that device without anybody else interfering with it. So that's important for that last step in the process, the evaluation process. Along the way, there are a lot of other tools that you might use. So we have sort of at the bottom here, we have kind of our interface, sort of initial interaction with the testbed resources. So things like Open on Demand and VNC sessions to do kind of GUI-based applications. Sort of coupled with Jupyter notebooks, we find that those are pretty useful. We'll talk about an example here in a second. Effective use of Python. Everyone who has worked with a testbed or has run one knows that it is kind of a struggle to help users, install and use the Python tools that they want. We feel like we have a pretty good story there where we kind of encourage people to do a progression. Start with a Python virtual environment. If you need to, maybe use Miniconda to install some things. And then if you need more than that, that probably means you need some package installed kind of globally. So sort of, reach out to the admins and work through that. One of the other things that we are actively developing and working on is container deployment. This is important because a lot of the tools themselves are difficult to build. A really good example is for the FPGA kind of RISC-V ecosystem. There's some really nice tools, like a simulation tool called FireSim and a chisel-based ecosystem for RISC-V out of Berkeley called Chipyard. It turns out those are actually kind of hard to build on an HPC cluster, and we find that students really struggle with that. But one thing that we've been able to do is to sort of encapsulate some of those into containers, and then also teach our users how to effectively use those containers for development. Okay, so I'm going to go through an example of a workflow, and the idea here is that this is probably one of our closest to production ready systems. It looks like an HPC system, but it has some interesting quirks to it. But this is just sort of an illustrative example to kind of gets you in the mindset of what we mean when we say, okay, a workflow for interacting with Novel architecture. This is the Lucado Pathfinder. This is effectively a very high performance graph analytics type system. And it has this really interesting characteristic. Instead of having a very large cache like you might see on a new AMD server, it actually says, okay, I'm gonna move my lightweight computation, my compute threads, to the data. And this system basically has almost no cache. I say almost no because the cores that run the OS and allow you to interact with it, those do have a little bit of cache, but all of the accelerators themselves have no cache within them. And you might say, okay, why would you do that? Well, it turns out that graph analytics they're not really cache friendly anyways. So this system actually is pretty good for things like if you're doing breadth first search, potentially if you're doing HPCG, there are sort of graph formulations of that. So I mentioned that the Pathfinder was on the Graph 500 and Green Graph 500 system. And part of that is because it's much more efficient than sort of a traditional cache-based architecture. I won't go too much into detail here, but basically this kind of looks like an HPC system with a few weird quirks. So for networking, it uses rapid I/O. Each sort of chassis, we call it, has a bunch of nodes, and within a node you have what are effectively like cores. So you have kind of your OS core, stationary core, and then you have your compute cores, which are actually doing the kind of low-level computation and interacting with memory. One of the really unique, interesting things about this system is that you can actually sort of reconfigure it. So you can say, I would like to run a job on a single node, where a single node has, let's say, 24 compute cores. Or you can say I might want to run on multiple nodes within a chassis. Each chassis has 8 nodes. We have 4 chassis total, so you could potentially scale up to a 32-node run. So you're kind of seeing this progression here if you remember that picture that I showed, and we will revisit it. But we talked about doing sort of a single node, or 1 to 2 node run, and then sort of mapping that up to a large scale 32 node run. The nice thing about this system is it is pretty close to production environment. We did work with the prototype system, the EmuChick, and that one, we wrote a few papers on it. It did have a lot of challenges in terms of programming. I think since then, there's been a lot of library and API support that's been added that really has improved the environment for our students and researchers. But the key thing to note is they sort of built on top of an open silk abstraction, and then they have sort of custom APIs for doing data layout. So there's a few unusual things, like they're using Yocto Linux in some places. The highest level sort of chassis nodes, those run like a Red Hat type environment with systemd. And it turns out we can install Slurm and run it on all of the PowerPC processors within the system. Although it did require some discussion and asking for certain libraries to be installed by the vendor. Okay, so if you think about how you access the system, we talked about scheduling being a key part of our workflow. This is a federated cluster. We have a big Slurm scheduler. This system is different enough that it actually has its own, little instance of a Slurm scheduler that it operates on. They all feed into sort of the same database, but this one is scheduled a little bit differently. So starting here from the left, we have sort of a command line access or an open on demand type interface that users can log into and sort of start to work on simulating and emulating some jobs. We have some x86 nodes that people can run some of these simulations and sort of emulation with x86 on. And then we have the Pathfinder system itself over here on the right. And so you'll see that it has 32 nodes, and then those can be scheduled in kind of a variety of ways. One of the big challenges that we found is that because the system is reconfigurable, Slurm does not really like that. It kind of assumes that when you make big changes to your system state, that the node is going to sort of reboot or reset itself. These nodes don't exactly do that. They kind of reconfigure, sort of some of the FPGA interface within each node, and so they don't work exactly correctly with Slurm for that reason. So this is definitely a challenge in terms of system maintenance and in terms of tools, but it's been a really interesting kind of exploration. Okay, so extending that, we take Slurm and we say, okay, we want to put Slurm on everything, and then we want to have open on demand that people can work with. This is very cool. I think this is very useful. It is also challenging. Right now, I think we have, I believe it's 10 or 11 different builds. So we actually had to go and write some Ansible playbooks to go and rebuild Slurm, every time we decided to do a release. So for instance, we're running 23.11. Turns out there was a point release that fixed a bug that we were seeing on a lot of our servers. But then we had to go and run that playbook and say, okay, please log into a RISC-V node and rebuild Slurm and re-symlink it. Log into a GPU node and do the same thing. But I think we've learned enough now that we know these are some of the pieces that we need to automate to be able to effectively run kind of a very heterogeneous system with different workflows. And this is just a picture of our open on demand kind of front end. So looks cool, like most open on demand front ends. Okay, so finally, wrapping up the workflows. So we have all these tools to interact with the system. And I had this initial sort of generic picture. The takeaway that I'd like you to get from this is that we know this is a complex workflow. We know this is not easy for new researchers to pick up and understand. But what we can do is we can say, okay, we can break this down, this complex workflow on the right. We can break this down to sort of our generic workflow and kind of give users small bite-sized instructions to jump from one step to the next. And I think we found with the students that have worked with this, that has been kind of a key piece to be able to enable them to sort of interact with and use these resources. So you have something like simulation, running at small scale, and then finally, reserving the entire Pathfinder system and running at scale. Okay. Are there any questions, or should I save those till the end?
We can save those till the end.
Okay, sounds good. All right, well, we'll speed along here. So the next thing I want to talk about is kind of education outreach. As I mentioned, this is sort of our beta testing of all the different pieces of the test bed. And one of the key things, going back to the Pathfinder, is that tutorials are kind of key to be able to get new researchers and especially students to be able to use some of these novel architectures. So we've done a bunch of different tutorials. I think the most recent one we did was a smart networking one at Supercomputing 2023. But early on, we kind of started with sort of the traditional HPC approaches, saying, okay, log into this system, open a terminal window and an editor, write some code, and then run that. And that kind of works, but I think what we found is that it was tough to engage a lot of the attendees because they didn't really have the appropriate skill level to kind of jump in there. So, what we've tried to do is sort of shift to what we have on the left-hand side here, which is sort of a Jupyter Notebook-driven workflow. So if you go to our GitHub website, it'll be at the end of this talk. You will see a bunch of our tutorials linked there, and one is this Lucada Pathfinder tutorial. And the nice thing is that we can kind of intersperse some of the content from slides. We still have slides, but we can take that and kind of intersperse it into these notebooks, along with sort of the commands needed to sort of simulate the application, and then also to launch and run Slurm jobs using the power of IPython and kind of different plugins. And we found that we get a lot better adoption when we have these interfaces, when we say, hey, if you're a tutorial user, log in via Open on Demand, open up this notebook, which we put in a convenient place for you, and at least go and like read through and run a few of the things and kind of understand some of the hands-on components a little better that way. So I think the user interface is key. So we're reinforcing probably what the open on demand people have been saying, for many years. One of the other things that we found is that in terms of venue, we do have to be a little bit careful about that because, I think we presented some tutorials, say at PERC and SC and HPEC and other places, and it really works better if you're kind of in an environment where, you're not cross-listed with a lot of topics that sort of overlap. So sometimes that can be the case, especially at a big conference like SC. Granted, you have a lot of people there, but some of the people who might be most interested in your topic are not able to attend. So, okay, so we have these tutorials. One thing we've done is we've kind of taken this and applied this to, our class infrastructure. So we have what's called a vertically integrated projects class, Future Computing with the Rogues Gallery. I think they made us name it that because of character limits or something. But we have a near memory subteam that focuses on the Pathfinder, and I'll talk in the next slide about some of the other subteams. But one of the things they've been able to do with these tutorial notebooks is to start there and then be able to look at benchmarks running on both the x86 systems and the Pathfinder system and kind of evaluate and compare those. We also have had students that have looked at sort of more advanced topics. Those are pretty complex, and I think really, those are tough for us as mentors sometimes to help students with, because, for instance, we had a project that was an operating systems design project, and it's been 20 years since I took that class. So we definitely can enable them to do some of these projects, but we also try to pair them up with appropriate mentors to make sure they're successful. One of the extensions from this class is that we've also found that this is a good way to sort of recruit student employees, basically research assistants and people to work on sort of different development tasks. At the left-hand side, we have a development task that we kind of had for students that came out of all this interaction with researchers via tutorials and students via classes. And one of the things we found is that people are saying, well, I just use a Google Calendar to schedule this resource. I kind of know how to use Slurm, but I just want to look and see who's using the resource and not have to run, SQ, and grep and figure out, who's using the resource and for how long. So we have a couple of projects like these where we are able to sort of think of interesting topics that students can work on that extend the capabilities and feature set of the testbed. I think this is probably a beta sort of feature that we have right now, but our idea is that over time, we might have a Google Calendar for each kind of class of resources that syncs via Slurm, with the Python script. Okay, revisiting the VIP class. I know I had a slide on that earlier, but I also wanted to mention some of the other teams that we have. So we have a couple pictures from the presentations that students do. They basically engage in a research project on one of 4 topics. So I mentioned near memory with the Lucada Pathfinder. We also have reconfigurable kind of RISC-V focus, neuromorphic, and quantum. Quantum was not something that we initially thought we were going to be doing, but it turns out because we didn't have a lot of classes in that area, we had a lot of students that showed up and said, "Hey, can I do quantum software development or quantum simulation?" So that's something we've kind of embraced and also tried to learn more about and understand better ourselves. But I think this program has been really good. Part of the really good part of this is that a lot of times students have the opportunity to maybe join a research lab and they interact with a small number of students there and the advisor. This is meant to be sort of multidisciplinary and also allow students to work for 3 or 4 semesters with the same team and kind of see progress through those semesters. And the really nice thing for us is when we look at our curriculum, I mentioned the quantum subteam, there are a few things that are sort of missing in our CS curriculum. So we've kind of slotted these classes into where we think they actually fit based on the prerequisites for students. For instance, we put processor design before the reconfig subteam, and part of that is because that team is looking, it's kind of assuming that you know a little bit about how a processor works. So if you can obviously join the team before then, but you have to do some background research to get up to speed to be able to kind of contribute to the project. But we think these are kind of cool. We know over time that there will be additional classes that fill in some of these sort of novel architecture curriculum gaps. But in the meantime, this VIP provides a really nice way to do that. We do have a paper down here at the bottom. Okay, and finally, one of the coolest things that I think we've been able to do is, support some of our existing classes. So we have kind of internal institutional, sort of funding that we can use to acquire and deploy new hardware for students. But we ran into this interesting situation with the pandemic, where anybody who's done any hardware purchasing in the past couple of years will know we had two specific issues. For us, one was that most of our students were not here; they were at home, calling in, and the other was supply chain. So previously, all our students would buy like a little pink board or a little Intel FPGA board and use it for one or two classes, specifically the processor design class that I mentioned. With nobody being on campus, it was really tough for us to figure out how to support that. So we said, how do we support a large number of students? And also, how do we think about ideas like data separation and privacy? So we had two courses. We had one that had 90 students and one that had 40 students. And I think we had probably about 40 to 48 of these pink Z2 boards. And we said, okay, what are the key requirements that we need to support these students? Obviously we couldn't deploy 130 boards because we didn't have that many. But as you can infer from some of the stuff we've been talking about, we just said, okay, these things, they have ARM cores, they run Ubuntu. We'll just put Slurm on that. So this is what that actually looked like. And there's a paper on this from STAHIT 22, where we worked with a bunch of people from our institutional computing unit, PACE, and then also locally within the college. But we had kind of two different environments. We had our PACE COC ICE, now just call them PACE ICE, which is like a traditional HPC cluster. And you could run the Xilinx tools on that. You could use a GUI interface to kind of interact and do some of that initial simulation and emulation part of the workflow. And then we had our pink cluster on the right-hand side here that was within the rogues gallery. And we sort of, they weren't really connected. There are efforts that we think now in the near future, we can probably connect them in some way. But at the time, we said, okay, this stuff on the left, COC ICE, and the rogues gallery, those are separate. And we sort of set up a kind of partition for classes that was secure for the students, but it was sort of on the students to move their data from the left to the right. So if you created a FPGA bitstream on the left-hand side, you would actually have to use something like rclone or Git to move that over to the right-hand side. But the idea is that we had this sort of large-scale resource on the left where you could do a lot of the work, and then we had a smaller but still appropriate size test bed on the right hand that students could interact with in a remote fashion. And so this led to, going from the left-hand side where we started, we said, okay, we can put a very small number of users on a VM. We can have them run all of the tools within the test bed itself. But if we think about 130 students, it's really tough to be able to support that. We might have said, okay, for a peak workload, I might need like 60 VMs. And that just gets crazy when you go and ask our IT department for that many resources for kind of a short-term use case. So instead, we went to sort of this workflow on the right, where students now can use ICE. You can put many more users per node. They can do most of their workflow there, and then they can copy over and run with like a Jupyter Notebook interface on the test bed. Okay, so we're coming to the end. So we think about all these things with education and novel workflows that we've worked on with the test bed, and some of the things that we're proud of and that we've had success about. One of the key things that we've noted with this testbed and with potentially tomorrow's supercomputers is that they are likely going to be extremely heterogeneous. Maybe not to the extent that this testbed is. I hope we are not running 10 versions of Slurm, but they definitely are going to have different components that require some of this thinking about how to sort of merge tools and sort of the different applications from different accelerators. So one of the things that we've looked at and that we've been really benefited from is a close relationship with PACE and working with some of the researchers there and thinking about how do we support heterogeneity via software and via operating systems. How do we take some of the next generation Slurm features, so things like node helpers and NSS, and using those for better container support and for supporting kind of the weird corner cases, like I mentioned, the reconfiguration of the Lucada Pathfinder. All those things are things that PACE also needs for different reasons. So if you look at something like an NVIDIA GPU with MIG support, that is also something that kind of mirrors some of the same setup that we have with the Lucada Pathfinder. And then finally, we both kind of realize that we need these better user interfaces. So we're looking at kind of a lot of different things. The biggest one I would say is probably stuff like, interesting hardware tools. So I mentioned a container with Chisel and sort of the RISC-V ecosystem for testing and designing RISC-V chips and accelerators. We do a lot of Apptainer. I think we are still working through some issues with that. On our test bed right now, we run Ubuntu 22 and Red Hat 8. PACE is making the move from Red Hat 7 to 9. So they're going to have a big jump in capability. And our goal as a test bed, as a much smaller test bed, is to try and mirror some of that high-level production support they have in our local environment. So then when users do stuff at a small scale, kind of like we mentioned in the workflow for the pink cluster, they can test stuff locally and then take it to the big cluster when that is appropriate. And one of the things we're starting to think about, I mentioned a lot of small things, so they all kind of come together into this one slide. So I mentioned this idea about, how do I move data between these resources? These are things that we're thinking about in terms of local resources. So we're kind of deploying a common storage that we can use both on PACE, on local workstations, and on things like the Rogue Salad testbed. Sort of looking at toolkits to deploy heterogeneous jobs. One thing that I think would be really cool is if you said, hey, I would love to run some portion of an AI workflow on a GPU node, maybe that's an NVIDIA GPU, and then I want to take all those A64FX nodes and use those for the visualization and kind of post-processing of the data. So you're kind of making effective use of different types of novel architectures in that case. And finally, I think the testbed is not fully integrated with Access resources, but definitely we want to kind of look at that and also sort of community services. So things like Globus Compute Endpoint, and Cyber Shuttle to let users kind of have a consistent environment so that they don't have to worry about the environment part. They just kind of worry about, okay, how do I sort of, where do I want to run my application? And where does it make the most sense to accelerate? Okay, so finally, I think there's a few things we learned. So, we say challenges. One of the key things that we learned is that you, and everyone probably can imagine this, at some point you get too many things and you say, okay, what things are people actually using? Part of that is the reason for investment in resources like Slurm, thinking about things like accounting. We have a good sense of what people are actively using within the testbed, but having, good scheduling and good numbers on, who is using which exact resource kind of tells us where we should dedicate our resources. I gave these great examples of building these sort of comprehensive workflows for the Lucada Pathfinder, but we can't do that for everything. So we kind of have to pick and choose our battles a little bit. So we want to be as heterogeneous as possible, but also, realize that we may need to sort of switch focus on kind of a yearly basis to target different things. One of the things that I hope you take away is that even though this is sort of a set of novel architectures and complex workflows, there are a lot of patterns that sort of cross each of these. And so if you can use some of those common tools, if you can kind of find the similarities from one architecture to another, that can make your job as kind of a system maintainer a lot easier. And potentially as a researcher, because then you can say, okay, I could run on this resource, or I could also use this one alternatively. Okay, so finally, just a few slides and I'll wrap up. Looking back at our figure, you might say, okay, where are we going to go from here? Well, obviously, we're just going to deploy a quantum computer. And I think one thing that we have found is that there are these sort of rogues or novel architectures that are 10 years into the future that are very exciting and very interesting. But there are a lot of things that are also very interesting in the short term. So where we might go in the near term, we're seeing a lot of investment in things like smart networking, seeing really cool deployments of additional APIs. So currently we're working with some of the MIT folks looking at graph plots on Bluefield DPUs, thinking about sort of larger platforms, both for like neuromorphic and potentially for something quantum related at some point. And most importantly, we're seeing that the tools are getting a lot better. So, the takeaway here is that it's not just this one piece at the bottom, it's kind of everything. All these things, a few of these things may seem much more complicated than others, but they're all sort of extremely heterogeneous, and we all need to consider them sort of as a whole in terms of how we approach different types of architectures, because there are a lot of similarities, and there are a lot of key pieces that we need to sort of enable these. And with that, I'll stop. I would say before I take questions, if you're interested, we have a project site and a GitHub page. So these slides will go up there and I'll share them in the appropriate way. You also can apply for access. This is a NSF testbed resource. Okay, thank you.
Thank you so much, Jeff. I'm not seeing any questions in the document yet, but if anyone has any questions for Jeff, please unmute and feel free to fire away.
Hey, this is Martin. Thanks, Jeff, for the presentation. I attended one of your workshops back, I think it was PERC a few years ago, and it was interesting. Very different programming and things like that compared to what I'm used to. I want to kind of ask how much impact do you see from all this? Because honestly, I went to the workshop and it was interesting, but I haven't really used anything that I learned in the workshop anywhere else in my work, So how do you somewhat see so what's your take on impact on these architectures, and what feedback do you get from other users? I mean, perhaps somebody goes and gets a job and one of the companies that develop these, I can see that's a big impact for them. But again, for our traditional people in HPC, do you have any connection or any sort of positive aspects of the people's further development in these architectures?
Yeah, I mean that's a great question, and thank you, Martin, and glad to see you again. So yeah, an experimental testbed like this, not everything is going to be winners, and ideally we would love to say we know this is going to be the future of neuromorphic computing or quantum computing, but we don't exactly know that. Ideally we're starting at the spot where a larger number of people can interact with something where it's not just like a simulation or something that is like an NDA'd piece of hardware that only one company cares about. But it's really meant to be sort of a place where we experiment with and evaluate and sort of determine for us, for our applications, is it a good fit? And I think some of the things people will say, yes, I think this is a very good fit. So a good example is with some of the smart networking stuff, we've had a couple different iterations of those. And we had, say, an older Mellanox card that had kind of a Xilinx FPGA that you had to sort of program at a low level. But we also have, more recent smart NICs that have ARM cores, Bluefields, or that have kind of high-level interfaces that you can interact with them. And I've heard from some of our researchers that these newer devices, they use the old ones and they said, man, that was painful. Like that is not a winner to me. Somebody might use it, but as an academic researcher, this is not valuable to me. But some of the newer sort of smart networking devices are very, very valuable to them. But you really don't know that until you test it out with specific applications. So, I think this is something we're trying to figure out as well. This is not something where we have this great amount of hardware and we know all the answers of what is going to be important. But we're trying to sort of provide the tools for researchers to benchmark and evaluate that. And I think if we're wise, what we would do over time is we would kind of say, okay, people are not using this resource, maybe we can keep it around, and if a few people are using it, we'll keep it active. But maybe we should invest more time in supporting, some other resource that a lot of people are interested in. Which at the moment I would say is probably FPGAs, AI accelerators, RISC-V. There's a lot of people that are sort of interested in those categories of things currently, but that might change.
So maybe follow up on this. So I can see a big utility of this for classes or for specific research that a professor from an institution might have an interest in one of these devices, right?
Mm-hmm.
So
yep.
I know you provide access to them, but how? I guess my question is how widely it's used, or how difficult it is then for a professor, say from Utah, to go and get an account at your center and have their class to run their things on your machines.
Yeah, we've hosted a lot of internal classes. I think it depends on the resource and the researchers. So it's very easy for researchers, individual researchers, to get access. And we have hosted, what we would consider like special topics. So those are typically, a small number of students from another university who are interested in one very specific resource. So say for instance, like a SmartNIC, with the Bluefields currently, we have kind of collaboration with some folks at BSC that I think will be used for some of their coursework stuff. For a large class, it kind of depends on the size of it. So I think definitely we'd be open to discussing that, but definitely we are able to kind of give access to most people who request it because it is an NSF resource. But that's different than saying, okay, we have enough people to support a class of 130 people. So the classes we do support are actually heavily dependent on the TAs that we have locally, that we kind of teach them how to maintain the infrastructure. So the stuff on the left-hand side of this picture here that I'm sharing that's the pink cluster, or part of it. And so the TAs actually have to know how to like reboot it and sort of understand a little bit about Slurm. So kind of a two-way street, I guess, but definitely be happy to discuss it if folks have ideas.
Any other questions?
Yeah, thank you for posting the links. Our GitHub has a lot of our slides and then also pointer to our Read the Docs and tutorials and stuff that we've done. So.
And then you're going to be putting these slides on that GitHub website as well?
Yes. Yeah. I'm happy to make them available. Otherwise, I saw one or two typos that I want to fix, but I'll make sure they get up there.
Yeah, I'm sure a lot of the folks on the call would love to take a peek at these slides and get a better picture at their own time. All right, well, with that, I want to respect everyone's time. So thank you again, Dr. Jeffrey Young, for presenting on the Rogues Gallery. And then I also want to thank Jim and Dory for helping out with the notes taking and keeping everything running smoothly on the back end. So this concludes our February call for systems facing track. Thank you all for coming, and hope to see you again next month.
Good. Thank you all.